We'll walk through an interesting problem here. In this problem, you have two bars AB and BC of lengths L and 2L as shown over here are rigidly joined at B, making an angle of 60 degrees and suspended by a string AD as shown in the figure. And we need to find what is the equilibrium position as defined by the angles if the weights of the bars are Q and 2Q. That is, this Q will act at a length of L by 2 from point A, and this 2Q will act at a point at a distance of L from point C. Okay. To solve this problem, we'll try to draw the free body diagram of the bars put together. Let me quickly try to bring up the free body diagram here. This is the free body diagram. You have three forces acting on it. One is this force Q here, and then the other force 2Q here, and then the tension in the string. Now quickly we can note that when you take moments about point A, this tension T will not have any contribution because it is passing through the point A. So the only two forces which will have any moment contributing to equilibrium are Q and 2Q. Okay, because this Q and 2Q are keeping the body in equilibrium, they need to lie on either side of point A. If one causes an anti-clockwise moment, for example 2Q here causes an anti-clockwise moment, Q must cause a clockwise moment to keep these two bars AB and BC in equilibrium. That is the first observation that we need to see straight from the figure here itself, even before drawing the free body diagram. And then draw the free body diagram to reflect that. That is, this force 2Q should lie on one side and Q should lie on the other side of the force A. So we'll try to write equation of equilibrium. That is, we'll note equilibrium condition as sum of moments about point A should be equal to 0. We are taking moments about point A here to see that this T does not come into picture. At least we are getting rid of one force. If you take moments about that, okay, to take that we need to have the perpendicular distances. So let me try to draw this little kind of geometry thing. Okay, so I'm drawing a horizontal line and then dropping perpendiculars. Oops, this didn't come well. Okay, and then I have extended this 2Q up to meet the horizontal line in E, and this point here I am designating as point F, and this point I am designating as point N, and this as point M. So if you take moments about point A, the perpendicular distance of the force 2Q from point A is AE. So we'll write 2Q times the distance AE should be equal to the perpendicular distance from point A to line of action of force Q is AF. So we'll write as AF. So the condition for equilibrium resulted in a geometric condition, okay, that this AE, twice of this AE must be equal to AF. Okay, from here onwards it is pure geometry. There is nothing more to it. Okay, so we'll note that this length AF We'll try to compute this length AF in terms of the lengths of the links AB and BC, and then the angles alpha and theta. Okay, so if you try to draw a horizontal line at point B, we'll see that this angle must also be equal to alpha. Okay, if this angle is equal to alpha, this big angle here, it must be equal to 60 minus alpha, that is theta minus alpha. If this angle is theta minus alpha, this should also be theta minus alpha. Okay, so this length AF should be equal to L over 2 cos 60 minus alpha. Okay, similarly we can find the length AE. AE we will write as NE minus AN, and your NE, you can very clearly see NE is L cos alpha minus AN. AN is L cos 60 minus alpha. So this condition, when you try to kind of simplify using elementary trigonometry, it comes in as L over 2 cos 60 minus alpha is twice maybe let me try to write it so that it doesn't go out of the screen. Let me try to move it a little bit here. So 2 times L cos alpha minus L cos 60 minus alpha. If you try to simplify it, you will get it as 5 times cos 60 minus alpha is 4 times cos alpha. If you further simplify that, you will get your condition for equilibrium. Tan alpha is square root of 3 by 5. Okay, you can see that in this problem you have two distinct steps. Step 1, an engineering mechanics step, wherein you applied condition for equilibrium to find out this as the condition, and step 2 is simplification, geometric simplification. We try to use a few simple rules of geometry to find what is the value of alpha. This is quite interesting problem, because we can actually build these bars AB and BC of lengths L and 2L making 60 degrees, try to suspend and find the angle alpha. And in fact this angle alpha comes very close to what we obtained here, pretty close. So it kind of gives an evidence that all the axioms we are following in engineering mechanics, they are in fact true in practice. We'll try to go to the next topic of defining a force and a moment as vector quantities in subsequent lessons.